Humans have explored almost every inch of Earth's surface, and with satellite imagery, we can even observe tough-to-reach places daily. But this outer shell makes up just a fraction of Earth. Its dense, hot guts are impossible to reach directly, and that's especially true for Earth's inner core. About the size of the planet Pluto, the inner core is made up of solid iron and helps power the magnetic field that protects life on Earth from harmful space radiation. But the inner core might not be as old as Earth itself. Analysis of titanomagnetite, a mineral that captures the strength of the surrounding magnetic fields when it crystallizes, showed that around 565 million years ago, Earth's magnetic field was drastically weaker, a mere 10% of its current strength. Over tens of millions of years, the magnetic dynamo strengthened to what we see today, likely from the formation of Earth's inner core. The inner core is a fairly recent discovery, geologically speaking, and scientists have been probing its secrets with various tools ever since. For centuries, people thought the Earth might be hollow or a burning, raging inferno. But by the early 20th century, researchers have settled on the idea of a layered planet made up of a thin crust, a thick viscous mantle, and a molten center. These layers were detected using seismic waves to X-ray Earth. After earthquakes or the explosion of bombs, two types of waves ripple through our planet. First come pressure, or P waves, followed by shear, or S waves. P waves can make their way through liquids and solids, but liquids stop S waves from spreading. Researchers in the 1900s detected a P wave on the other side of Earth after they bent and refracted through the Earth's interior. By contrast, the S waves never made it through. That led scientists to think that Earth's core was entirely liquid. However, this theory was challenged when Inge Lehmann, a Danish seismologist, noticed a P wave in an unexpected place. Lehmann concluded that it had to have bounced off of something dense, something solid, and the idea of Earth's center was born, a solid inner core suspended in a liquid outer core. More recently, researchers have made another discovery: routes where P waves travel at greater speeds, particularly along Earth's north-south axis. Changes in these fast lanes hint at the existence of an innermost core, nestled inside the inner core. Researchers estimate that it's roughly 600 kilometers in diameter and slightly offset from the planet's center. Yet many questions still remain about its composition and how it formed. Seismic waves of a different type have led researchers to believe that the inner core might spin at a different rate than Earth itself. Nuclear tests, which can be located more precisely than earthquakes, have helped researchers understand the inner core's rotation. In 1971 and 1974, the Soviet Union detonated 2 atomic bombs underground in the Arctic. By comparing the waves that bounced off the inner core from these tests, researchers found that the inner core rotated slightly faster than the planet. But analysis of 2 earlier bomb-induced earthquakes in 1969 and 1971, this time set off by the US military under Alaska's Aleutian Islands, showed a different trend. The inner core rotated slower than the planet in this time period. While a change in the rotation speed is likely, other researchers think the differences in how these seismic waves travel are due to the surface of the inner core changing shapes. Beyond studying seismic waves, researchers are also attempting to recreate the inner core's extreme temperature and pressure inside the lab. Tests range from using shockwave experiments to pressing and heating iron between diamond anvils. These experiments hope to get a glimpse of the molecular structure of iron in the inner core, and one of these studies suggests that the solid inner core may actually be rather